So today we are discussing about the system suitability parameters. So basic requirements USP, several parameters that are integral part of the chromatography which are used to verify that the chromatographic system is adequate for the intended analysis. There are the several definitions in the chapter which are essential to understand the concepts of the chromatographic system. So among them some parameters we are discussing over here. So first one, that is a tailing factor. Tailing factor is nothing but it is also called as a symmetric factor. So theory assumes that ideal symmetric peak, which is known as a Gaussian peak, the front side deviation from the Gaussian peak is known as a peak fronting, or the rear side deviation known as a peak tailing. So peak tailing or peak fronting, these are two concepts which are regarding your tailing factor. It is the factor which describes the shape of the chromatographic peak, and it is a measure of the peak tailing. So distance from the front slope of the peak to the back slope of the peak divided by the twice distance from the center line of the peak to the front slope, with all the measurements made at 5% of the maximum peak height. As per USP and EP, tailing factor is determined as AS is equal to width of the peak height at 1/20th of peak height of D, or the H distance between the perpendicular drop from the height. So peak maxima to the base. So this diagram shows the clear cut idea about the tailing factor, that is AB is equal to BC upon CA. So TAB is equal to AB upon twice of AC. So 10% of peak height and 5% of the peak height. These are the some deviations, or this describes the how much tailing is occurs within your diagram. So theoretical plates, it is another factor. How many number of the theoretical plate, it's which also explains the efficiency of the column, or affect the column efficiency. So Martins and Singe use the chromatographic model involving hypothetical division of the column into two number of plates known as the theoretical plate. So theoretical plate is an imaginary part of the column. The theoretical plate number is the measure of the efficiency per unit length of the column. The larger the theoretical plate number, the sharper the peaks. So number of the theoretical plates N is equal to 16th TR upon WB square. So this is the basic formula for determining the how many number of the theoretical plates are present within the columns as per the theory. So within the diagram, first one, that is the column. So this column is divided into various types of the plates, and based on that there is a formula for determination of the number of theoretical plates. Then next factor, that is a signal to noise ratio. So signal to noise ratio, it is not the response of our analyte or solute. So it is a response of the solvent. So it is an unnecessary response from the detector. So the short-term noise influences the precision of quantification. So SUN ratio, that is a signal to noise ratio, is useful system suitability parameter to identify noise effect on the quantification of impurities. So basically the impurities are interpreted by using this signal to noise ratio. So 2H upon H, it is the formula for determining signal to noise ratio. The height constant peak measured from the peak apex to the base extrapolated over the distance 25 times the peak width at its half height. So it is the give the basic idea about the signal to noise ratio. The next factor, that is a resolution factor. So resolution means that is the isolation or separation of the two peaks. So the ratio of the separation of the band maxima to their average base width, baseline resolution achieved at R is equal to 1.5, but more than 2 is also considered, or it is also desirable. We can relate the resolution to the number of plates in the column, the selectivity factor, and the retention factor of the two solutes. So it is a factor R is equal to 2 TR2 minus TR1 upon WB2 plus WB1. So baseline resolution achieved at R is equal to 1.5, but more than it gives the desirable reading. So capacity or retention factor, it is the next factor. So it is the migration rate of the analyte on the column. It is the measure of here the peak of the interest is located with respect to the oid volume. The measure of the time the sample component resides in the stationary phase related to the time resides in the mobile phase. It is the ratio of the adjusted retention volume and hold of the or void volume. So capacity or retention factor is completely depends on the retention time or retention time of the analyte or the retention time of the mobile phase. So the formula is given as K is equal to TR minus TR minus T naught upon T naught. So it is a height K value and lower K value. So this is the K interpret, that is a capacity or retention factor. The next factor, that is the selectivity factor or the relative retention. It describes the separation of the two species on the column. The relative retention of the two peaks in the chromatogram is also called as a selectivity. So relative retention of two peaks is called selectivity because of this is the separation of the two species on the column. So the graph is completely gives an idea about the how many times of the peak references are given here, and the relative retention alpha is equal to it is denoted by the alpha. So alpha is equal to TR2 dash upon a TR1 dash. So K2 upon a K1, that is a selectivity factor, or it is also called as a selectivity. The next one, that is the peak to valley ratio. So peak to valley ratio may be implied as a system suitability criteria in the test for related substances when baseline separation between the two peaks is not achieved. Means there is the emerging